Lightwave Communications Laboratory was established by Professor Liang Quan-Chen when he joined Department of Information Engineering in 1992. Now we have two professors in our lab, Professor Liang Quan-Chen and Professor Chung Kit-Chan. Also, we have 7 PhD students, 1 M.Phil student and 1 research assistant doing research in our lab. Professor Chen received the Bachelor of Science degree in Electrical Engineering from National Taiwan University in 1983 and the MS and PhD degree in Electrical Engineering from Columbia University in 1992. He joined the faculty of Department of Information Engineering, the Chinese University of Hong Kong, and established the Lightwave Communications Laboratory in 1992. He was the department chairman in 2004 to 2006. In 2007 to 2013, he was a member of the engineering panel of Hong Kong Government Research Grant Council. He is a senior member of IEEE Photonics Society and Communications Society and a member of OSA. He has served as an associate editor of IEEE Photonics Technology Letters from 2005 to 2011 and OSA IEEE Journal of Optical Communications and Networking from 2012 to 2015. Among graduated students, 2 PhD students and 1 master's student have been selected for the Youth 1000 Talents program. Professor Chan received his Bachelor of Engineering M.Phil. and PhD degrees from the Chinese University of Hong Kong, all in Information Engineering. Upon graduation, he joined the Department of Electronic Engineering at the City University of Hong Kong as a research assistant professor. In August 2001, he joined Department of Information Engineering at the Chinese University of Hong Kong and now serves as a professor. Now, he is department chairman. He has served as members of the technical program committees of many international conferences including OFC, NFOEC, OECC, etc. He was an associate editor for OSA Journal of Optical Networking and IEEE OSA Journal of Optical Communications and Networking. He served as the chairman for IEEE Photonics Society Hong Kong chapter during 2012 to 2013. Dr. Chen has published more than 200 technical papers in refereed international journals and conferences, 2 book chapters on passive optical networks and 1 edited book on optical performance monitoring. He holds 2 issued U.S. patents. Optical camera communication is a kind of visible light communication that uses camera as the receiver. The potential application of this technique includes information broadcasting, vehicle-to-vehicle communication and indoor positioning. For most of the CMOS sensors, pixels are activated row by row, which is termed rolling shutter effect. Benefiting from this effect, if we modulate the LED light much faster than the frame rate, multiple LED states can be captured on one frame. At the transmitter side, the transmission data are generated from the computer and then uploaded to the FPGA. Then, the FPGA and the driving circuit will drive the 5 RGB LEDs. At the receiver side, the optical lens can focus the light on the CMOS sensor. It is believed that in 2021, the smartphone user will amount to 3.8 billion all over the world. Therefore, the smartphone embedded with CMOS cameras will become the largest optical receivers readily available for optical communication. Optical wireless communication has drawn great attention for various applications, such as high-speed indoor communications and intelligent transportation systems. In recent years, there is an increasing demand for marine resource exploration and environment monitoring. Visible light communication, especially using blue light, has potential applications for underwater wireless communication for its unique advantages over the radio frequency signals and acoustic communications. It can reach tens of gigabits data rates and hundreds of meters. However, the environment-induced impairments, such as the air bubble and turbulence effect, are the most challenging issues for these scenarios. This is a laboratory setup of underwater optical wireless communication affected by the air bubbles. We can see the fluctuation of received optical power. Novel schemes can be proposed to mitigate those impairments induced by the environment and boost the throughput of the VLC system. The system you are looking at now is a Brillouin Optical Time Domain Analyzer, or BOTDA for simplicity. This system is based on stimulated Brillouin scattering, which is a nonlinear effect in optical fiber. The basic principle is that when two optical signals with a certain frequency difference opposite propagating, there will be a power transfer from the signal with higher frequency to lower frequency one. Next you will see the demonstration. As we scan the frequency over the target frequency, you can see the amplitude of the pink signal is amplified and the gain reaches its peak when the frequency gap is just equal to the target frequency. The value of target frequency is affected by the environmental temperature and strain, so that we can distinguish the temperature or strain changing by observing the peak gain shifting. Thus, this system can be used as a temperature or strain sensor in reality.